right, 8.4, derivatives of log functions. So recall back to lesson 8.2, we learned that the derivative of e to the x was just e to the x. And there was another little law that we didn't really cover in 8.2, but you should be aware of, that the derivative, so what happens if we are looking at an exponential function that doesn't have a base of b? Okay, so his derivative is actually b to the power of x ln b. Okay, so those are those derivatives. And now when we look at the log functions, so we looked at what a natural log was in the 8.3 lesson. So this ln x is just a log of base e. This derivative is 1 on x. If I don't have a base of e, then notice how you have this extra piece. Okay, ln b is just a number, but be aware of it. Okay, I'm going to just do the proof to the first one. Okay, and I would encourage you, once you see the process, to try it on the second one where the base is b. It also works. Okay, so the first thing for the proof of ln x is we're going to let y equal to ln x, which is really the same as log of base e, right? That's what the natural logarithm means. And then I'm going to convert this into exponential form. So this would be e to the power of y is equal to x. And now I'm going to take the derivative. Okay, so what is the derivative of e to the power of y? Equals x. So we're actually going to end up having to do implicit differentiation on this. So e to the power of something, its derivative is e to the same, right? Followed up by, when that argument's not x, followed up by its derivative. So that's going to be y prime is equal to the derivative of x, which is 1. And then we isolate for y prime. So there's a little bit of implicit going on here. So we get 1 over e to the power of y. But what do I know about this? I know that x is equal to e to the power of y. So by substitution, then y prime is 1 on x, which is the derivative that you are given up here in your box. All right, so again, you could give it a try with this one as well, where the base is b, and you would have to use this little piece of information about knowing the derivative of b to the x or b to the y or whatever. All right, so let's try some of these knowing these rules. So what would be the derivative of y equals x ln x? So we have a product here. So y prime is going to be 1 d2, so the derivative of ln x is 1 on x, plus 2, which is ln x, d1, and the derivative of x is 1. So this is just our lovely little song, 1d2 plus 2d1, the product rule is so much fun. And then we can see that we could tidy this up. The x's here are going to cancel, and then that just leaves me with 1 plus ln x. And that's it. That's all you got to do for that one. All right, next one. So this one has more going on inside than just an x. So back in our little box, it says, well, what happens if you have this u thing, right? It's not just x. Then you have to do the chain, okay? So we have 1 on u followed by the derivative of the argument, okay? That's what we're going to need to do on this question. So this is your u piece, right? So it's the derivative, let's just write out this row, of ln u is equal to 1 on u du dx, okay? So this is d outer, d inner. Don't forget your dinner. Okay. So let's do this. Change colors. So y prime is going to be 1 on u being x cubed plus 1. And then we have to take the derivative of the inside, which would be 3x squared, right? So we have our d outer, and then we have our d inner. And then when we tidy that up, the 3x squared can just become the numerator. And that one's done. Okay, here we have what if f of x is equal to absolute x, ln absolute x. So first of all, I'm going to rewrite my f of x function in its piecewise definition because I have an absolute value. So you have to remember this guy is a piecewise function. So what does this mean? This original function before we take the derivative is going to be ln of negative x when x is less than 0, and it's going to be ln of positive x when x is greater than 0, and x is not going to be allowed to be equal to 0 because it's a log function. Okay, we can't take the log of 0. And remember, if you're putting in negative x into this function, we're actually ending up to take the, so x is negative 4, right? So it's negative 4. That's what ends up happening, right? We get the, we get them negatives canceling out. All right, so now we can take the derivative of the piecewise. So f prime of x. I actually have lots of room, so I'm going to go down below, sorry. Okay, so f prime of x is going to be, so what's the derivative of ln negative x? So it's 1 over the argument multiplied by the derivative of the argument for x less than 0. And then ln x's derivative is just 1 on x for x greater than 0. And what I would notice is that top function is actually, let's just erase this x less than 0 for a second. This top function actually tidies up to 1 on x for x less than 0. So since those two things match, okay, then I can then say that the derivative is in fact just 1 on x, but x of course cannot equal to 0. All right, example number 4. The derivative of ln sine x. So throwing in some trig stuff here. So y prime is equal to 1 on the argument when it's a logarithm, a natural logarithm, multiplied by the derivative of the argument. So what's the derivative of sine? The derivative is cos. So we have cos on sine. So think about that. Cos on sine is equal to cotan. So whenever you're working with trig, see if you can simplify to a more simplified trig expression function. All right, number 5. So we have a chain here. So y prime is going to be 4 multiplied by ln x reduced by 1. That's your d outer. Okay. And then we have to take the derivative of just the inside, which is 1 on x. And then we would say, could we tidy this up in any way? Well, not particularly. There is a different way we could write where that 3 goes. So we could write this as 4 ln cubed x, all ln x. So there's not a lot we could do with that one. Okay, number 6. So we got ln of a really crazy argument. So method 1 of this would be to use your chain rule and your quotient rule. So we'll look at that first. So the derivative of this is going to be equal to, so 1 on the argument, ugly, ugly, like this. and that's the one on u part, and then followed up with the derivative of the argument. So we've got our d outer, and now we have to do the quotient rule for the inside stuff. So we've got 1, which is, sorry, not 1, that's product rule, sorry, d, so low d high, less high d low. I have to think about my rules, my rhymes. Okay, so low, I'm going to just write this as x minus 2 to the half. Low d high, so the derivative of x plus 1 is 1, less high, x plus 1, d low, so I want to take the derivative of x minus 2 to the half. So we're going to put the half in the front, x minus 2 reduced by 1, and follow up with the derivative of the inside, which is just 1. Whew, that's ugly. Draw a line, and down below, square it shall go. So here it goes. Whew. And now the calculus part is done. There's your dinner. It's quite a hefty dinner. Okay, so now we have to try and tidy this up. Let's see what we can do. So first of all, this front guy is going to flip. And so let's do that. And then what's going to happen over on this other side? So do we have a common factor on the top? And we have a fraction. So I'm going to pull out that half. I'm going to pull out x minus 2 to the negative half. That's pull out the one with the lowest exponent. So if I take a half out of this front part, right? So 1 divided by a half, that's going to give me a 2 here. Okay? And then I would be dividing this x minus 2 to the half by x minus 2 to the negative a half. That's going to leave me with x minus 2. Okay, and then I have subtract. The x minus 2 piece here is going to go away. That part's going to go away, leave me with my x plus 1. Okay, brackets. And we still have this bottom piece. Now, when you square that, you're going to get x minus 2. And what do we got left? So let's expand out that bottom. And what do we get here? So we're going to have 1/2. This is a negative exponent, so he could actually go to the bottom. And this would leave me with 2x minus 4 minus x minus 1. And so I have an x minus 2 to the half and an x minus 2 on the bottom. And what that'll allow is that x minus 2 to the half can cancel. That half, actually, the 2 could go down below as well. So what are we left with in our numerator then? We have 2x minus x, so just x, and then a negative 4 minus 1, which is a minus 5. And on the bottom, I have my 2 for my half, and I have x plus 1, x minus 2. There it is, all tidied up. Whew! Fun stuff, guys. That brings back memories of chapter 2. Do you remember chapter 2? It's been a while. Okay, so the second method of doing this is actually 100% easier. Think about this as we transition to the next video. How could we use laws of logarithms to determine this derivative rather than what we just did, rather than the craziness that we just went through? Is there a way we could use our laws to simplify this? I'll see you back, video number 2.